Oh, we're on. Okay, good. Now, I'm sorry, that last one when I was kind of clicking around, that was probably frustrating as hell. But anyway, so let's take a look at this problem. So this is what we're talking about. We've got the filament of an incandescent lamp. All right. And we'll get the formula for write an equation for the initial current that flows through the filament when it is initially turned on. In other words, when it's still at room temperature, which we're going to assume T naught is equal to 293 degrees, 293 kelvins, and it's going to heat up to almost 10 times that, to 28. Some of you have a much higher Kelvin temperature than that, or it might be a little bit lower. But they gave us 4.4 times 10 to the negative 3 kelvins to the minus 1 is the thermal coefficient of resistivity. And so what are we talking about here? So let me write down for this problem where V is equal to 75 volts and I, that's after it's been running for a while, I is equal to 0.75 amps, because as that, because here's what's going on physically, here's what happens. As the resistance goes up, the voltage doesn't change. That's the amount of the voltage power supply going into this light bulb is only 75 volts. That doesn't change. So that means the resistance is going to go up. So what does that do to the current? It goes down. So that's a drop in current. So let's just take a look at what they're talking about here exactly. Okay. So here we go. So here's what they want. They want to know when we usually do it this way, where we say, well, the resistance afterwards, the resistance after it's heated up, R final, is equal to R naught, R original, times 1 plus the thermal resistivity of the thing times delta T. Okay? That's what we're talking about. And we know that our resistance in general, just a general statement of resistance, is equal to rho times L over A. Okay, and so we've also got this. We know that and so as it heats up, this coefficient of resistivity goes up. All right, so the coefficient of resistivity is going up, and it's equal to this. It's equal to rho naught times 1 plus that thermal coefficient of resistivity times delta T. All right, so that's what they're trying to get you to see, and to know that L over A is going to cancel, because we know that V, which is going to stay constant, is equal to I naught times well, the initial times R naught, which is also going to equal I, after it's heated up, times R final. And if I put in these values for, if I go, well, I naught is equal to R, which is equal to rho naught times L over A, which is equal to I, which is after it's heated up, which is the value that they gave us. This I is the 0.75, is equal to I times rho final, times L over A. All right, well, the L's over A cancel, so I've got I naught rho is equal to I times rho with that relationship to the temperature. All right, this guy. And so I can plug that in, and I get I naught is equal to I times, and I'm plugging this, goes here. It is equal to rho naught times 1 plus that alpha times delta T, close that parentheses, divided by rho naught. Aha! The rho naughts cancel. And so I naught is equal to I times 1 plus that alpha times that change in temperature. Which in this case is the 2800 minus 293. Okay? And you're going to get a pretty big current when you do that. And then I think the next part is probably pretty easy. And that's what they're after. I think they want us to put in I times parentheses. Do they at least let us put in the row? No, 1 plus. Now, I haven't done this yet. Do I get my little alpha? Yep, times alpha times T minus T naught. Close. Incorrect answer. Kiss my. Oh, I forgot to close. I need one more parentheses. Now let's try it. There we go. See? Need a human being. Uh-oh, I did it for you. But now, find the numerical value of the current in amps when the filament is at room temperature. Okay, so now you just plug that in. So that's the beauty of actually doing a formula. All right, out here on that one.